Okay, the next question we are looking at is the generating voltmeter. And this generating voltmeter is an interesting voltmeter.
Every single day, I'm gonna make something great. That's my way.
So this is the image of the generating voltmeter. And what is a generating voltmeter? We did discuss this. We mentioned that a generating voltmeter is a variable capacitor, which is also an electrostatic voltmeter, voltage generator, which generates current proportional to the applied voltage. So it generates the current that is proportional to the applied external voltage. So if we can measure this current, then we can know using the proportionality, the value of the external voltage, and that is the way it measures. Now, how it varies the capacitance is by its design. So this design has got these plates, if you can see the spaces in here, and these plates cover up these spaces here on the fixed plates or the electrodes. So this rotates, the S0 rotates, and because it's got variable spaces where plates are missing in these sections, this creates the variability of the capacitance. And that variability of capacitance now creates, we can determine the current from that variability of capacitance, and then knowing that the current is proportional to the voltage, then the measurement that we get from the current ammeter, microammeter here, means that we can get the reading of the voltmeter. Now, like I mentioned, because these are two plates, so it is also acting as a variable capacitor. So these capacitance values are going to vary, and we expect them to vary mostly to have a sinusoidal effect in terms of variation of that capacitance. Now, let's see what this implies. So first of all, we know that the capacitor stores charges, and we can determine that charge through CV, and the current through the capacitor then can be determined. Current I through the capacitance can be determined by dq dt. That's the rate of change of charge, and this can be calculated as d CV over, which is, we are replacing now the charge to be CV over the rate of change of time, which implies that we can now separate these to have C dV dt plus V dC dt. V dC dt. Okay, so we are saying the current now is C dV dt plus V dC dt. Okay, now for a DC voltage, we know that for DC voltage, what you are experiencing is that dV dt is going to be equal to 0. And from this, we can therefore say the current now comes only V dC dt. And we know that the capacitance C varies from C0 to Cm, meaning that the capacitance is going to charge to full, so from the initial value to the maximum value of capacitance. And the voltmeter measures DC, so the generation so the generator generates AC, which is converted to DC using the diode in the circuit, as we saw in the circuit. Now, moving further, we are able to now determine that the current I is equal to VDC dt, which is equal to the capacitance changing from minimum or from the given value, so d dt, and then we have now C0 plus C maximum sine omega t. Okay, and this gives us this is similar to V0 plus Cm cos. So after we take the differential there, the differential of the constant is 0, then we have the cos there, omega t, omega. Okay, having done that, therefore our current is going to be equal to V omega Cm cos omega t. That's our current value. Or we can say the current is equal to the maximum current cos omega t. So Im then, the maximum value of current is going to be equal to V omega Cm. That is our Im. Okay, so if we can determine the maximum current value on that curve, on that the peak maximum current, and this is important because in the calculations we're using the RMS value of current for us to determine to solve the generating voltmeter questions. And for this reason, what we have is the RMS value, IRMS value is equal to Im over root 2. And this implies that our Im is V omega Cm over the square root of 2. And we are saying the RMS value is direct proportional to the voltage, okay, while omega stays constant. Okay, and this is the more reason why when we come to the question, we will see that what we are using is this IRMS value, and this is how we come up with this current value. Okay, so when we get back to the question, we are saying this is the current value, the RMS value, and that is how we determine this. So this is coming from the RMS value being equal to Im, which, if you remember, our Im is equal to V omega Cm, and our RMS value is Im over root of 2. So we come up with that, and we've been asked to find the capacitance. So the question says a generating voltmeter is required to measure voltage between 15 kV to 250 kV. If the indicating meter reads a minimum current of 2 microamps and a maximum of 35 microamps, you are to determine the capacitance of the generating voltmeter. Assume that the speed of driving synchronous motor is 1500 RPM. So we have the speed of the synchronous motor indicated in that way. Now, if we come to also understanding one section of this, is that apart from understanding the equation, so we've understood this equation, that is how we are coming up with RMS value in that sense. But also we must understand where this is coming from. Where is this coming from? That is 2 pi times 1/5 over 60. 1/5 being the synchronous speed of the motor. So when we come to this, we must understand that the synchronous speed of a motor, Ns, is equal to 120 multiplied by frequency over the number of poles. Okay, so this gives us 1,500 RPM that we have, revs per minute. But then our rotational speed, N, omega, is 2 pi Ns over 60. So this is what we have as our rotational speed. So in this case, our rotational speed is 2 pi multiplied by the speed that we've been given, in this case to be 1,500 over 60. This gives us the omega that we have. So therefore, when we come to the question that we are dealing with, we are saying for us to determine the capacitance value, okay, we are coming from the IRMS to be equal to V omega Cm over root 2. And our question is to find the capacitance value, which is Cm. So we convert the capacitance value, and then our omega is this omega now, which is 2 pi 1/5 over 60. That's our omega value. And this is how this is coming up. So in our equation, we've got the IRMS given. So we take the minimum value of the current provided. So in this case, we've been given the IRMS, which is 2 microamps, and then we've been given omega. So our omega, this is now part of our omega in the circuit. So this is our omega. So you've got, then we pick the minimum value of the voltage given as V. So V omega, so this is 15,000 volts multiplied by Cm multiplied by omega. This is our omega. This is root 2, and therefore we determine our Cm to be equal to 1.5 picofarads. Okay, and that is how we determine that. Okay, 1.5 picofarads. Now, in some cases, you may be asked to also determine the capacitance of the generating voltmeter. So this is the capacitance of the generating voltmeter. But you may be asked to find now the actual current. Okay, the actual current now that you've determined the capacitance. So in that case, now and then you have to determine the actual current at the value. Let's say in this question we've been given 15 kV, which has a minimum current that we use as 2 microamps, and then we are not so sure if this is the maximum current, but we can determine it using this 250 kV that we've been given to determine what is the maximum current after we have determined the value of the capacitance now. Okay, and that means you simply plug in the details in the equation, and that will mean that for this case you have your IRMS being equal to VCM omega over root 2. And you've been given your V now is 250 kV. So 250 multiplied by Cm. Cm, you just found it as 1.5 picofarads, so times 10 to the power negative 12. That's the picofarad. And then this over root 2 multiplied by the omega. So you've got 2 pi multiplied by 1500 over 60. And you determine now the actual IRMS value that you obtain, that is for the voltage level, the peak voltage level of 250 kV. Okay, so you do your calculations there, you solve that and determine it in microamps. Okay, so this is all about generating voltmeter. In the notes, I think we've done a good description of what a generating voltmeter is. This is just a tutorial of how you solve questions related to this. And the questions just play in terms of values. So you may be asked to find the voltage, you may be asked to find the maximum capacitance or the capacitance of the generating voltmeter, and so forth. Okay, and so this is how you handle questions related to generating voltmeter. I have another example, but it's very similar to this one, so I reckon there's no need to go through the same procedure that we've done. I hope this is clear to you. Thank you.
Dear friends, thank you for watching this channel. Subscribe to the channel for more. Thank you. Have a good day.